Hey guys, welcome. So we are on to lab, what is this, lab 5? Right, okay. Share my screen. We're gonna be talking about ISO. So, isokinetic dynamometry. Wow, that's a mouthful. Don't worry about it. I'll explain it a little bit more. But yeah, this was a kind of fun one to do in lab. I forgot to change the fall 2020 thing again. It's spring 2021. Anyway, I'm gonna first talk about, we're gonna get it right into it, but I'm gonna first talk about sliding filament theory, and then we're gonna talk about the force velocity relationship, and then length tension relationship, and then we'll talk about force and power, and then how strength differs with fiber types. I'll talk about the methods of the experiment. We will not do purpose statement hypothesis. You guys watch the methods video and then calculations afterwards. And yeah, pretty quick. Yeah, you can't see John Cena in this one. My face is probably covering him, but oh. Okay. So, sliding filament theory. We kind of went over this last week in EMG, but basically I'm just going to briefly go over it again. Sarcomere, remember, sarcomere is the smallest contractile unit, so it is the like this right here. So the actin and myosin like working together, the contractile unit. Cross bridge is the connection between actin and myosin. So it's that little like right here, this little area where they meet. And this is essentially just the sliding filament theory. I think Dr. Cotter, he sent us, at least the graduate students, he sent us a really interesting article on the sliding filament theory that was published like last month or something like that. So I will also include that into your content section. You can see my little dog here, the corner of the screen. She's annoying my other little dog. Hey, come here. Oh, yeah. Dog life. Okay. Anyway, so what even is isokinetic dynamometry? That mouthful of like words. It's really easy. So ISO, we're gonna like break it down. ISO means same, and kinetic means speed or movement. So it's just the same speed or movement. So basically, here's Dr. Cotter. I love this picture because he's like very like intense, like he's very concentrated on what he's doing, and it's just like very funny to me to look at him like that. This is an isokinetic dynamometer. It is not the one that we have in our lab right now, but it's very similar. It has like the little chair and this little thing that you strap your leg to, and it has like a little thing like for your like a point basically where your leg moves and stuff. So anyway, isokinetic dynamometry or dynamometers, they make sure that whatever movement you're doing is performed at the same speed. So it controls for your speed, and it measures the amount of force that is produced while you're doing that movement. And yeah, so, and it has a number of different speeds. We'll go more into it when we get into the actual methods of the experiment. Okay, force velocity. I'm pretty sure you guys have already been introduced to this, but I'm going to briefly go over it. Force velocity, you can see the visual representation of it, of this graph. So force velocity curve, it kind of looks like this little downward slope right here. But this right here, this full like left and side of the right side of the graph, it shows you the relationship between the different contractilities. So concentric and eccentric and isometric. So you can see the concentric over here on the right side. Eccentric is going to be on the left side, and then iso is going to be right in the middle of this line right here. So there's the reason why this is happening is because isometric, you're not moving at all. So like there is no velocity in no movement. So yeah, and basically for concentric, you can see right here as velocity increases, the amount of force that you can produce decreases. And that is, think of like if you put on your 1 RM for your back squat, you're not going to be able to go super fast or as fast as you could if you did like your 20 RM, you know? But yeah, so for eccentric contractions, it's slow velocity is low force. So think about like, I always do the bicep curl like example, but think about like you're doing a bicep curl, and this bicep curl is you're like holding way more weight than you can do. It's going to bring your arm down, right? It's going to like lengthen your muscle. But if you put a ridiculous amount of weight like in your bicep curl, it's going to bring it down faster. So like as the weight increases, the velocity also increases. So it's the opposite essentially of the concentric. So slow velocity, low force, fast velocity, greater force. That makes sense. Basically, just think of it as the opposite of concentric. Okay, so this is the length tension curve. And basically, right here, it shows you the sarcomere, like the unit. And it's essentially what it's saying is that there's like a perfect length of a sarcomere. And this like perfect length allows for like optimum like force production. So right here, you can see like basically it's completely smushed. There's not like much more it can contract. Like when you've got like your arm like this, you can't contract your arm more because like it's smooshed. You can't go any further. And so you're not going to be able to produce a lot of force like this. So like this, yeah, no, you can't do it. And then the second one up here, it's a little bit more like lengthened, but it's still not great, but better than this. Right here is your optimal length. So probably like this would be your optimal length, like something that's not super stretched out, something that's not like too close in together. And this optimal length will allow you to use all of your cross bridges and be able to produce the maximum amount of force. While this right here, as you lengthen it out, you're gonna have fewer cross bridges to like pull from. So it's going to be less force. You can produce less force because it's just like, you know, when you're holding on to something like with the tip of your fingers, like you're not going to be able to hold on to it for very long, especially if it's heavy, if you're only holding on to the tip of your fingers. But if you have more of it, if you have like more of it grasped, then you can like hold on to it for longer or like hold on to it because like you have more surface that you can hold on to. That's essentially the same thing with the sarcomere. So like the little actins and myosins are like the tips of their fingers, so they can't like, you know, grab onto it as strong as they could right here at the optimum perfect length. Let's see, more cross bridges is more force production. Concentric at high velocity, not too much overlap, not enough cross bridges. Yeah, eccentric, high velocity, less time for cross bridges to disconnect, passive tension. Yeah, basically what I was talking about. Okay, so I know this like is kind of this is very much biomechanics stuff, and I'm not going to go into it because I don't need to. But I'll just briefly talk about it. Torque is basically force required to rotate on an object, so like force times momentum arm, and you can see a visual of this momentum arm, like force times momentum arm is torque. Peak power is at 30% of concentric torque, so right here. I think Dr. Cotter drew this out on one of his lectures, but I'm not sure. Basically, so peak power is 30% of concentric torque. Essentially, like your peak power is going to be at 30% of your force production. And power is force times velocity. Yep. And then this is kind of like an example. This is kind of let you guys see how different like resistance training is related. So hypertrophy for like strength and power training, hypertrophy, that's not going to be like a whole lot of force production, but it's going to be a lot of load right here. You see the reps per set, and then the sets, that's going to be pretty high load, while strength is going to be high force, so high intensity, low load. And then power, it's going to be high intensity, also low load. But it's different because the amount of load that you can do for strength is going to be a lot more than the amount you can do for power because of this 30% like peak power thing. Excuse me. So now we're going to kind of get into more of applications for the experiment. Ipsilateral and bilateral. Ipsilateral is the same. So think of, I don't know for ipsilateral. Bilateral, think of two, both. So ipsilateral, same side of the body, same limb. So your agonist versus antagonist. Agonist, let's say it's the quads, and antagonist is the hamstrings. You're just measuring to see like the strength between the two muscles. So like if your hamstrings and quads are equally strong, they're going to have a ratio of 1. If your hamstrings are stronger than your quads, they're going to have a number higher than 1. If the hamstrings are weaker than your quads, then you're going to have a number less than 1. And the range is generally from 0.5 to 0.75. So your hamstrings are usually weaker than your quads, which can lead to like injuries like ACL tears. Bilateral, both sides of the body. So 2 limbs. So you're measuring your right leg from your left leg. And if there's a 10 to 15% difference, there's a very much increase, a significant increase in injury, risk of injury. So I want you guys to remember these 2 terms because we are going to basically be using them in this lab. Okay, so muscle fiber types. You guys have probably already gone over this, type 1 and type 2 muscle fibers. And then I don't know if Dr. Cotter uses this particular figure. I'm pretty sure my face is probably covering up part of it. but you could probably see the fibers down here. And then this is the neuron, like the motor unit, basically. Both of these is neuron and the fibers together is the motor unit. Remember last week? Okay. Anyway, these kind of represent the muscle fiber types. So you can see this small like fibers right here. This is your slow oxidative. So slow twitch. This is going to be your type 1 muscle fibers. And then right here, this like motor unit with a bunch of fibers is going to be your fast glycolytic, which is going to be your type 2 muscle fibers. And I don't think I have, yeah, so into more of a description of it. Basically, your type 1 and type 2 characteristics are going to be defined by how fast they are, their twitch time, how fast they are, twitch time, and then size of the motor neuron, force production, fatigability, so how fast they fatigue, and then their aerobic, anaerobic activity. So type 1 is going to be your aerobic fibers. It's going to be fatigue resistant, so it's going to be able to last for longer. It has a lot of mitochondria because it's aerobic. It doesn't produce a lot of force, and it has like a slow twitch time. In like real speed, they're really fast, but like compared to type 2, they're slow. And they have a smaller motor neuron like was shown in this little picture right here. Type 2 muscle fibers. These are your anaerobic fibers, so they're going to have fewer mitochondria because they're not going to need them. They're going to have a greater force and power output. They're going to be fast compared to your type 1 muscle fibers, and they're going to have the large motor neurons. Okay, so these are the experiments that we're going to do. Experiment 1, 2, and 3. Experiment 1, we're basically going to be looking at like the force velocity curve. We're going to be getting the force velocity curve on one side of the body using all of these different velocities. Experiment 2, we're going to determine ipsilateral and bilateral strength. So ipsilateral, same limb. We're going to be measuring between the quads and the hamstrings. Sorry, that was my phone. And then bilateral, we're going to be measuring between the left and the right leg. And experiment 3 is going to be your fiber type makeup. So we're going to be doing the Thorstensen fatigue test. That one always trips me up. But basically, we're going to have them do 50 reps at a particular speed and see their fatigability, essentially. And then not doing the statement and hypothesis. Watch your videos. Just, yeah, do that. So to help you with your Excel sheet and your calculations, Dom has a video. I've already posted it on Beachboard, so you can go watch that. Okay, exam 2. It's next week. Don't forget about it. I feel like exam 1 just happened, but yeah. Prepare for that. If you have any questions about it, please ask me. And yeah, remember that this lab is not due next week. It's not due during exam week. It's due the week after. So don't worry about this until like after your exam. I want you guys to focus on your exam. Okay. All right. So if you guys have any questions, please let me know. But thank you for watching.